Classification of elements is based on the periodic law. It gave us a method to organize the known elements in such a manner that the physical and chemical properties of the said elements could be analyzed in a systematic way. Moreover, it showed us a way to synthesize new elements. The first real effort to classify elements was formulated by a German chemist Johann Wolfgang Dobryna in the year 1829 through his law of triads. He made several groups of 3 elements, the middle one having atomic weight and also the properties almost intermediate of the other 2. This law did not work for all the elements and did not gain the faith and popularity. The next attempt was made by a French geologist A.E.B. Duchoscouftois in 1862. He noticed the periodicity of elements when they were ordered according to their increasing atomic weights. Periodicity means similarity in properties after a certain period. The elements were arranged in the form of a spiral on a cylinder. Similar property elements were found to be lined up vertically. He called this telluric helix because the element tellurium was placed in the middle of the spiral. His system of classification did not work because of the following reasons. It used more geological terms than chemical terms. The chart included some ions and compounds in addition to elements. There was no diagram as such. The next attempt was made by English chemist John Alexander Newlands in 1865. He also arranged the elements in the order of increasing atomic weights and introduced it through his law of octaves. This law stated that when the elements are arranged in order by increasing atomic weights, the 8th element from a given one will have similar properties. He compared it with the 8 notes of the octave of music. What he published in 1866 was something of this sort, and it was ridiculed by other chemists. The reason was quite obvious, but one thing is for sure, that the core idea of the periodic law had been planted in the minds of the contemporary scientists. Then a German chemist named Julius Lothar Meyer independently worked on the periodic table and published his work in 1864. His work comprised of 28 elements only, and the main basis of classification was the valence of a particular element. Later on, he published a periodic table which more or less resembled the table which was published by Russian scientist Dmitry Mendeleev. Dmitry Mendeleev was given the main credit behind the preparation of the modern periodic table as of now. Mendeleev spent much time in arranging the then known elements. He actually played a card game of solitaire, with each card having the name of an element and its atomic weight written on it. While arranging the cards, he gave priority to the properties like valency rather than the atomic weights. First, he placed hydrogen at the top of the table over here. Then lithium was placed below it because it had the same valency as hydrogen, and he wanted to keep the elements with similar properties in the same column, which he named groups. Then he kept on placing the cards like this. At this stage, he found that sodium had similar properties when compared to lithium, so he placed sodium over here in a new row. He then continued with his work. At this point, after calcium, he couldn't find elements having similar properties with aluminum and silicon, so he left them blank. Then he found arsenic similar to phosphorus and placed it below phosphorus. Then selenium was placed here and bromine was placed below chlorine. Now these elements were left out. What to do with these elements? These were called transition elements and these were called typical elements. What he did? He divided these 7 groups into subgroups A and B like this. He then placed the transition elements in the subgroup along with typical elements. In the first 2 groups, the transition elements were placed in the B subgroup. and in the other groups they were placed in the A subgroup. The properties of typical elements of the second row did not match with the transition elements but matched very well with the typical elements. Now still these three are remaining. What to do with these three? He placed them in a separate group, that is group 8. He then continued with his work. The transition elements had a horizontal relationship of properties, or in other words, the property of these elements had similarity. The typical elements, however, had vertical or periodic relationship. He struggled to give the then known rare earth elements like erbium, yttrium, cerium, thorium, lanthanum, didymium a place in his table. In fact, didymium was not an element at all. It was a mixture of praseodymium and neodymium. The atomic weights of these elements were also wrong, and the position given to them was wrong as well. He left a whole row blank and placed the elements like this. He then continued with his work and got a periodic table like this in the year 1871. You see that over here iodine, which had a symbol J at that time, was kept under group 7 and tellurium was kept in group 6, although tellurium had a greater atomic weight. He predicted that the atomic weight of tellurium should be lesser, which was not true at all. He also corrected the atomic weights of elements like beryllium and indium and many others. Beryllium had an equivalent weight 4.5 and was considered trivalent because of its similarity with aluminum. Thus, beryllium was considered having atomic weights 13.5, but there was no place for beryllium in the table. Mendeleev considered beryllium bivalent from the empirical formula of its oxide and corrected its atomic weight from 13.5 to 9, which was later found to be correct. Same thing happened with indium. Indium was considered to be bivalent because of its occurrence with zinc in minerals and was considered to have atomic weight 76, which was twice its equivalent weight 38. But there was no place for indium at that position. Mendeleev proved it to be trivalent and corrected its atomic weight from 76 to 114, which was later found to be correct. After arranging all the 63 elements known at that time, he found many vacant spaces left in his table. The excellence of Mendeleev came into play. He said that the missing positions were actually vacant because elements were still undiscovered. This was found to be true as many elements were discovered later on, which fit into the gaps of Mendeleev's table. Mendeleev even named them as Eka boron, Eka aluminum, and Eka silicon and predicted their properties. Later on, scandium, gallium, and germanium were discovered and found to have almost all the properties that were predicted by Mendeleev. At the end of the 19th century, the noble gases were discovered. They were given a separate group called the group 0. Later on, when newer elements were discovered, they were given appropriate positions. The rare earth elements were also given positions at the same place over here due to their similarity, which was of course horizontal relationship. Since they were very large in number, they were given a separate place outside the main table like this.